Assalamualaikum warahmatullahi wabarakatuh. My name is USWAH binti Muhammad RAZAK, and today I am going to present my topic, which is synchrotron radiation, its principles and application. So we go first to the introduction of synchrotron radiation. What is synchrotron radiation? It is an electromagnetic radiation that emits when charged particles, such as electrons, are accelerated in a circular or helical trajectory. It is generated in synchrotrons, which is a large circular particle accelerators designed to produce this unique type of light. Why is it important? Synchrotron radiation is distinguished by its extreme brightness, broad spectrum ranging from infrared to hard X-ray, and highly collimated natures. It enables insights into atomic and molecular world that are impossible with conventional light sources. For historical perspective, synchrotron discovered in 1947 at General Electric's laboratory. It is evolved from a byproduct of particle accelerators to a powerful tool for research and industry. So how does a synchrotron works? So before that, we need to know the important parts of synchrotron. It consists of electron gun, linac, booster ring, synchrotron beam, storage ring, beam lines, optic hatch, experimental hatch, and lastly workstation. So we look at the step-by-step process of how a synchrotron works. First, the electron source. Electrons were emitted by an electron gun and accelerated using a linear accelerator, linac. And then, electrons are further accelerated to near light speed at the booster ring. And then, from there, we go to the storage ring, where electrons are injected into storage ring, where they are kept circulating by magnetic fields. As electrons are deflected by magnets in the storage ring, they emit synchrotron radiation. The radiation is directed along the beam lines to experimental stations for various analyses. The key components in synchrotron are magnets, RF cavities, and vacuum chambers. Magnets guide and focus the electron beam, while RF cavities maintain electron energy levels. And lastly, vacuum chambers prevent scattering of electrons by air molecule. Synchrotron shows its unique properties of radiation. The first one is its brightness. It has millions of times brighter than traditional X-ray sources, enabling a detailed imaging at an atomic level. It also has broad spectrum that covers a wide energy range from infrared to hard X-ray, allowing versatile application across disciplines. It also has high collimation and coherence. It produces highly directional and coherent beams, ideal for techniques such as X-ray diffraction and spectroscopy, and it also has polarization control. It is linear or circular polarization of the light can be tuned for specific experiment. So for applications of synchrotron, it is very useful in medical imaging. In this article, it explains how synchrotron X-ray radiation is used in microangiography. Microangiography is basically it's just like a conventional X-ray that we use on our bones, but for microangiography, it is an X-ray image for our vessel systems. So from this article, they said that they use single energy temporal subtraction method to emphasize blood vessel contrast by subtracting pre-contrast image from post-contrast image using single energy X-ray just above the iodine KH. The iodine KH is another method of medical imaging. The articles also further explain the advantages of SR microangiography. It has the ability to visualize coronary and pulmonary microvessels in small animals through intact chest walls, something that conventional X-ray system cannot achieve. However, there are several risks like complications from arterial catheterizations, but it is mitigated using contrast injection, but the dilution of contrast before reaching coronary arteries can be a limitation. This method has been successfully applied in animal studies, capturing high-resolution image at 30 frames per second, which enables detailed visualization of microcirculation. It shows promise for diagnosing coronary disease with improved clarity and precision. Another application of synchrotron is in energy sector. Synchrotron radiation tracks the formation of solid electrolyte interface (SEI) layers, which protect the battery but can also degrade it. The gas bubble inside the battery helps separate the electrolyte from the electrode, making it easier to see the SEI layer clearly using soft X-ray absorption spectroscopy. This soft X-ray absorption spectroscopy get its source light from synchrotron radiation. This technique can detect chemical changes in the SEI, which helps track degradation. The method helps scientists understand how the SEI deteriorates over time due to factors like electrolyte breakdown and lithium loss, which can cause battery performance issues. By using this approach, researchers can gather detailed data to improve the stability and lifespan of batteries, helping develop more efficient and long-lasting batteries. So for Malaysia's synchrotron potential, for current status, Malaysia currently lacks a synchrotron facility. Researchers rely on collaborations with regional facilities such as the Synchrotron Light Research Institute in Thailand. So for future prospect, building a synchrotron in Malaysia could accelerate local advancement in agriculture, medicine and industry. Investment in training programs and international partnerships is essential. So as a summary for this topic, we covered how synchrotron radiation is a powerful tool with application in fields like biology, medicines and material science. Its unique properties make it indispensable for high-resolution imaging and structural analysis. Why it matters? Because continued investment in synchrotron technology will drive innovation and address global changes.